So stop me if you've heard this one before. A big computer costing hundreds of thousands of dollars, running a special programming language fine-tuned for big AI programs. And these programs can replace human experts, process military information, and do advanced math. Sounds familiar, no? Except this all happened 4 decades ago. In the 1980s, a new industry of cult AI computers emerged amidst an AI boom, the largest of which generated millions of dollars before it all came crashing down. For today's video, some say it's the finest programming environment ever created, and that its users only gave it up when PC silicon got 50,000 times faster. All we know is, it's called a Lisp machine! But first, I want to remind you about the Asianometry Patreon. Early access members get to see new videos first with selected references attached. I'm working hard to organize and annotate the references to make them more useful. Early access really helps a lot and is one of the best ways to support the channel. I deeply appreciate all of you. Thank you, and on with the show. Our story begins with John McCarthy, one of the greatest pioneers in both the computer science and artificial intelligence fields. He apparently coined the phrase artificial intelligence whilst writing up the budget proposal for what turned out to be a very famous research project at Dartmouth in the summer of 1956. That is quite a trivia to hang your hat upon. That Dartmouth research project worked as like a symposium, with several contributors presenting papers and interesting projects. One of the presentations featured the famed computer science researchers Herbert Simon and Alan Newell. They were the only ones with a working program. They presented a program which was able to prove 38 theorems from a book called Principia Mathematica, and for this it's been called the first AI program. Simon, Newell, and their collaborator Clifford Shaw went on to produce other groundbreaking AI programs like General Problem Solver. Their approach towards human intelligence was known as symbolic AI. This philosophy asserts that since the brain cannot directly access the outside world, it must create abstract, internal representations of the real world in order to navigate it. Thusly, everything we know and think about is guided by an internal representation made from symbols. Intelligence is nothing but the making of, modifying of, and destroying of these symbols. And if our brains can do it, then so can our computers. So programmers create symbols to represent a thing and then handcraft a series of rules called heuristics to manipulate those symbols. In this symbolic approach to AI, researchers examine the logic behind or end results of a particular behavior, and then translate that into a series of steps for the computer to follow. Several years later, this symbolic or good old-fashioned AI approach won out as the preferred paradigm of replicating human behavior in the computer. I covered an alternative approach centered on a neural network type structure called a perceptron in a prior video. Simon, Newell, and Shaw described a programming language they created and used for logic theorists, Information Processing Language or IPL. IPL came from the trio's dissatisfaction with existing programming languages like IBM's Fortran. They believed that human thought was about producing and editing associations between different symbols in the form of ideas or memories. The issue was that Fortran and BASIC demanded that we predefine and reserve our arrays and data structures in memory before running the program. So the programmer must know everything the program will do ahead of time. To Simon, Newell, and Shaw, this was not how the human brain worked. IPL, which ran on an early computer owned by the RAND Corporation called the JONIAC, supported this with lists. Imagine data in memory organized like beads on a string. Each bead will hold additional information pointing the user to the next bead on the string. That's a list. The trio first got the idea for what was called list processing from magnetic drum memory machines, which were very old forms of memory, and they discussed it in detail with John McCarthy during the summer conference at Dartmouth. Now, McCarthy liked the idea of list processing. He felt that lists can more easily represent symbolic data structures like trees and formulas. However, he did not want to copy IPL because it depended on a unique hardware feature of the one-of-a-kind Johnny-Act computer at the Rand Corporation. There was also another idea that McCarthy wanted to implement. In these early days, most computers computed numbers. That was their focus. But McCarthy had been playing with IBM's new language, Fortran, and liked how it allowed you to write programs in a more algebraic style. In this way, you can take complex formulas or logical statements, cut bits and pieces off of them, and manipulate them. Thusly, you can apply a function to another function just like as if you were multiplying two numbers. In the fall of 1958, McCarthy took these concepts and worked with his grad student Steve Russell to create the first implementation of the Lisp programming language, short for Lisp processor or Lisp processing, not quite sure which. As a non-programmer, I hesitate to try and put into words why Lisp enthusiasts like this language so much. But I must try, because otherwise it would be hard to understand why people love Lisp so much as to build an entire machine dedicated to it. Maybe I can start by constructing a list of a few things about Lisp. Lisp is all about simplicity. One can argue that a Lisp program is organized as a set of functions that call one another. All objects in Lisp, both code and data, are expressed as lists that can grow or shrink, ideal for representing objects that can change as a program executes. Lisp programs can take code as their inputs and output new programs, something called metaprogramming. Such features make it easy for programmers to model complex processes like those of human thought. The language is also easy to learn. The syntax is uniform and consistent, with a parentheses prolific structure that facilitates the heavy use of recursion. No need to memorize quirky, arbitrary language features, though I do see people on the internet complain about the profusion of parentheses. And finally, Lisp is quite extensible, so users can easily extend the language to create variants. This was as much a minus as a plus. A serious impediment to Lisp adoption in the early days was its sheer number of dialects. But I must admit that my list rather shortchanges the love that enthusiasts have for Lisp. Paul Graham is a writer and investor, more known for co-founding the Y Combinator startup accelerator, but he appears to really like Lisp too, having written about it for many years. In one essay that I particularly enjoyed called The Roots of Lisp, Graham argued that Lisp is minimalist and elegant, computation broken down to a few fundamental building blocks, but at the same time, it can scale to whatever the programmer might imagine. In creating Lisp, McCarthy forever changed how computers were programmed, and it's arguably not even his most famous achievement in computer history. The man literally invented time-sharing. Lisp quickly caught on with the young AI crowd at MIT's AI Lab, where McCarthy first worked, before disseminating out to other AI groups at universities around the world. Starting in the late 1950s, the United States government started funding and nurturing AI development. This was done particularly through DARPA, the Defense Department's R&D center. Created in the wake of the Sputnik fiasco, DARPA's goal was to do cutting-edge research to ensure America's technological superiority. In 1962, their Information Processing Techniques Office, or IPTO, hired the famed psychologist J.C.R. Licklider as its director. He was there for just 2 years, but influenced policy for decades thereafter. Licklider believed that computers can be true creative partners with humanity, working side by side to augment human intelligence. To fulfill this vision, machines need to be more capable, flexible, and intelligent in interacting with humans. He funneled money into artificial intelligence and computer science research at universities on both the East and West coasts, the military reasoning for such being that advanced AIs would be key in next-generation command and control systems. By the way, the repercussions of Lick's research vision are felt far and wide today. The projects he funded helped bring us the graphical user interface and ARPANET, an ancestor of the modern internet. That's something to put on your resume. Anyway, DARPA's support legitimized AI as a research field, and early on funding came with little specific pressure for commercialization, giving researchers freedom to explore and cross-pollinate. Large advances were made in speech recognition, computer vision, and expert systems. One major issue with Lisp back then was that what made it such a pleasure to program in also made it rather difficult for the hardware of the time to run it. In those days, before the rise of things like semiconductor DRAM, computer memory cost thousands of dollars. Thanks to its extensive Lisp use, Lisp was a very memory-hungry language that was a pain to run on traditional mini-computers like the PDP-10 or VAX, both produced by the company DEC. These computers had minuscule amounts of RAM that users can access, a phrase called address space. Early variants of the PDP-10 had about 256 kilowords. Words, the term, referring to a fixed unit of data that the processor can handle in a single operation. In the PDP-10, a word was 36 bits, so 256,000 words was about 1 megabyte today. In Lisp, lists are made up of nodes of two pointers, a pointer pointing to the list element and another to the next item on the list. Each node uses a word, limiting the total number of list nodes that the computer can hold in RAM before needing to swap it out to the hard disk drive. State-of-the-art AI programs of the 1970s and 1980s called expert systems, remember that name, regularly had tens or even hundreds of thousands of nodes. To help ameliorate this, Lisp offered an automatic memory management feature called garbage collection. It triggered whenever the computer ran out of memory, working its way through lists of objects and freeing memory for reallocation. But early iterations did not work that well, and on top of that, this was the age of time sharing, so researchers had to share that limited memory with 20 or so other users. Waiting hours for a computer to slowly turn its way through a program drove these young researchers crazy, and it soon led them to create their own hardware. In 1973, a researcher named Richard Greenblatt started the Lisp Machine project. He cited as inspiration a paper written by Peter Deutsch of Xerox PARC, which proposed to create a mini-computer that could run the special microcode for Lisp. Greenblatt's project began as a simple software emulator for the PDP-10, emulating how a Lisp machine might work. Greenblatt was then joined by a colleague named Tom Knight, and together they requested funding to build an actual machine. Stephen Lukasik, who then worked at DARPA, then called ARPA, recalls in an oral history receiving the request in 1973. He said, "I put it in the budget because I thought it was a good idea. And the reason I thought it was a good idea was because I was interested in AI, and I felt that if you give the researchers better facilities, they'll, of course, work faster. I mean, if you're slugging out some artificial intelligence on a general-purpose, time-shared computer, don't expect to make as much progress as if I give you a $100,000 or $200,000 special Lisp machine." The single-user Lisp machine computer was powered by a general-purpose processor reprogrammed at the microcode level. It was called cons, short for construct, a function within Lisp to produce a data structure like a list. If we want to be pedantic, then cons specifically describes the microprocessor. The Lisp machine in question includes both the cons chip and the accompanying special microcode. But for the sake of brevity, I shall call the whole thing cons. Greenblatt intended cons for his own use and so stuffed it with a wish list of things he cared for. This degree of hardware customization, particularly for a higher level language like Lisp, was rather unusual. What are some of these customizations? A notable one was its tagged architecture. Like as the aforementioned PDP-10, cons process words of 36 bits. The majority of those bits carried the data, with the remaining minority set aside for tagging. Why do that? Lisp is dynamically typed, so a variable can be set to an integer, to a string, to another list per your sauciest desires. When running operations, it is important to keep track of these types so not to accidentally add a letter to a number and crash the program. Cons tags made it easier to do that. Cons also featured an operating system entirely written in Lisp, allowing programs and the OS to communicate in ways that some considered to be unnatural. There was also a graphical user interface with windows that can be manipulated with mice. The resulting machine was a true pleasure for Lisp developers to work in. Cons impressed DARPA enough that Greenblatt got money to build a few more for other MIT teams. Then teams outside of MIT got interested and bought some machines for about $50,000 or about $285,000 today. In 1977, Greenblatt and his team created a second computer called CADR. The naming is another in-joke. In the Lisp language, the CADR function retrieves the second item and more of a list. That function's unusual name is derived from CDR, or contents of the decrement part of the register, which comes from the IBM 704 computer that Lisp was originally developed on. The CADR was largely the same as cons, but had a few improvements. This included microcoded data type checks and a better garbage collection system that worked in real time without pausing the whole machine. CADR got a lot of attention and became a rather significant hardware-making operation at MIT. As Greenblatt recalls, they offered to make one for anyone with at least $50,000 in their budget, and eventually they made about 35 CADRs. The success was public enough that in 1979, the MIT lab's former director Russell Nofsker approached Richard Greenblatt about possibly starting a business around CADR. At the time, artificial intelligence seemed like it had a rich future. Nofsker felt that the market of hardware-accelerated software had potential, but wanted Greenblatt's support since he was the guy leading the team literally building these machines by hand. Greenblatt was amenable, but wanted the venture to be wholly bootstrapped, a company run by hackers for hackers, getting his ultimate hacker machine to other hackers. It would have the same informal culture as the MIT AI lab, just making cool stuff for themselves and their ilk with no money men telling them what to do. Nofsker thought differently. He wanted a professional company with managers, salespeople, bathing/hygiene, and venture capital funding. This split led to two companies spinning off from the MIT AI lab, Nofsker with Symbolics Inc. and Greenblatt Lisp Machines Inc. or LMI. There are a number of perspectives about this split. Greenblatt was a bit sanguine, recounting it in an oral history for the Computer History Museum. Anyway, I wanted to do this bootstrap thing. They didn't, and there were a number of other differences, shall we say. So, what ultimately wound up happening was the two companies split out. Both licensed the software from MIT. The majority of the original team, I'm afraid, went with Symbolics. A few people stayed at MIT, and the few people that stayed at MIT sort of actively helped LMI, in particular RMS. This RMS is Richard Stallman, who is known for founding the GNU project as well as his advocacy of free software. Stallman worked on the cons and CADR projects and recounted in a rather entertaining 2002 speech, Greenblatt then recruited Russell Nofsker, the man who had hired me, who had subsequently left the AI lab and created a successful company. Russell was believed to have an aptitude for business. He demonstrated this aptitude for business by saying to the other people in the group, "Let's ditch Greenblatt, forget his ideas, and we'll make another company," stabbing in the back, clearly a real businessman. Those people decided they would form a company called Symbolics. They would get outside investment, not have scruples, and do everything possible to win. But Greenblatt didn't give up. He and the few people loyal to him decided to start Lisp Machines Inc. anyway and go ahead with their plans. And what do you know? They succeeded. A former Symbolics employee named Dan Weinreb disputes this history in a comment posted onto Dan Liu's blog. I highly recommend that you read both the statement and the blog post, as it is an excellent first-person overview. Weinreb said that it was unrealistic to found and run a computer company without outside funding, and that the members of the Lisp Machine project at MIT had doubts about Greenblatt's ability to successfully head and run such a business. Fair enough, I reckon. In the book The Brainmakers by H.P. Nyquist, an excellent recounting of this saga and more, Nofsker recalled that he begged and pleaded with Greenblatt to change his mind and eventually gave up. Getting that VC funding took some time, but let Nofsker and Symbolics set up a well-stocked lab right across the street from the MIT lab. Paychecks, flexible working time, and available computer time, it was all a very attractive package to these students. And as for Greenblatt, he lucked out. Symbolics took some time to get off the ground due to delays in getting venture capital funding, and then in 1980 he met Alex Jacobson, a consultant for Control Data Corporation who had been looking at natural language processing for teaching students. Jacobson helped Greenblatt make a business plan for LMI, find angel investors, and even source the first sale from Control Data Corporation. This split seems to elicit some strong feelings, maybe even today. The LMI people regularly accuse the Symbolics people of being unethical, quote-unquote stealing software, and violating the quote-unquote hacker ethos and the law. And the Symbolics people, in turn, being incredulous at all this and upholding their reputation. Good vibes all around. Symbolics and LMI had very similar products at the outset. Symbolics' first computer was the LM2, which due to funding delays launched only in September 1981. So LMI, despite starting later, actually launched a product first, the $100,000 LMI CADR. Adhering to Greenblatt's pledge, they ran on self-generated cash flow, essentially building Lisp machines to order. Their first year, 1980, the company made $1 million selling to Control Data and Texas Instruments. With both the LM2 and LMI CADR based on the original MIT CADR computer, the two companies sought to quickly move to their second-generation Lisp machines, Symbolics to their 3600 symbol processing system, and LMI their LMI Lambda. It is important to note that the two basically ran the same software stack. Both Symbolics and LMI bought a software license from MIT for the Lisp flavor, OS, text editor, and utilities. The deal let them modify and improve the code so long as they passed those improvements back to MIT. This means the two companies largely needed to compete on the basis of their hardware, its integration with the software, and how fast they can implement new software features before those features enter the quote-unquote common stack. The core target market for these $100,000 to $140,000 computers were universities, corporate research labs, and government. This market was driven by blossoming hype in the early 1980s surrounding a particular AI, expert systems. I briefly mentioned them earlier. They are rules-based AIs following a different approach. Rather than trying to be general problem solvers that struggled with complex real-world scenarios, these expert systems try to capture and replicate the knowledge of experts like engineers or doctors. They have two major components, a knowledge base and a control/inference engine. A knowledge base is basically a huge bunch of lists containing domain-specific facts and rules of thumb gleaned from the aforementioned human expert by human workers called knowledge engineers. You can imagine the things within these lists as something like sophisticated if-else statements, possibly paired with a probability analysis. The expert system's inference engine then takes a group of assumptions and circumstances and runs quote-unquote inference on its knowledge base to conclude on something, like the possible presence of a copper deposit. Widely popularized by Edward Feigenbaum of Stanford University, who had been a former student of Herbert Simon, expert systems were seen as democratizing knowledge and potentially, maybe, replacing expensive human consultants. Notable examples include Prospector, a geological expert system produced by SRI International, the guys who also made Siri. Prospector helped determine the existence of mineral deposits, and it was successfully used to identify a molybdenum deposit in Washington state, presumably for making EUV Bragg reflectors. The tool never made it to production, but was nevertheless featured in various media stories. Businessweek featured it in a 1984 story titled Artificial Intelligence is Here. The story begins by saying, and I quote with a few slight edits, "After digging dozens of small mines and drilling hundreds of test borings, they were still hunting for the elusive metal 60 years later. Then just a couple of years ago, miners hit pay dirt. They finally found the ore because they were guided not by a geologist wielding his rock hammer, but by a computer located hundreds of miles to the south in Menlo Park. This dramatic feat was the first demonstration that revolutionary kinds of computerized helpers called expert systems could have vast commercial potential, proving once and for all that research in AI had become more than a laboratory curiosity." "It's ironic," says Randall Davis, a professor of AI at MIT. 3 years ago, AI was considered flaky. Now it's hot, and everyone wants in." The timing referred to in that quote is interesting. Since the beginning, government spending had been a major driver in AI research and thus the Lisp machine industry. But in the mid-1980s, DARPA spending surged. Some of this was tied to the Strategic Defense Initiative, the space-based missile defense system that critics so derisively called Star Wars. But more than that, there was also an ambitious program called the Strategic Computing Program that DARPA pitched to Congress and the military. Its backers believed that AI products like expert systems, natural language understanding, and computer vision were on the cusp of being incorporated into military systems. The effort would research new VLSI tech, chip designs, computer architectures, and AI software to close the existing gap. As always, this push also involved a dose of Asian geopolitics. In late 1981, the Japanese government announced a new cross-organization initiative called the Fifth Generation Computer Systems Project. The project was to explore new forms of computers, software-guided human-machine interaction, and AI for the next decade. More practically, they explored non-von Neumann parallel hardware and AI programs, eschewing Lisp in favor of another language called Prolog. An admirable goal, but one that came at the wrong time, the very height of the Japanese economic scare in the United States. Many people fixated on the funding, an unprecedented $500 million at announcement, but in some reports inflated to $4 billion of quote-unquote public support. Others narrowed in on the possibility of AI-powered robots taking people's jobs. Long story short, American observers saw the fifth generation computer project as Japan challenging American supremacy in computers. That Japan was going to do again what it already did in cars, electronics, and so on. Feigenbaum himself wrote a book about the project, somewhat playing into this narrative. Of course, in the end, it didn't turn out like that, but I shall reserve the whole story for another video. Nevertheless, that fear produced lavish government funding for American AI projects like expert systems. Over $1 billion would go into machine intelligence research between 1983 and 1993, fueling Lisp machine sales. But it was recognized from the start by people within Symbolics that their machines needed to do more than just AI. And in their original 1981 business plan, Symbolics laid out their intentions to also compete in medical advisory, genetic engineering, Symbolics mathematics work, and semiconductor design. The focus on semiconductor design was interesting. The plan talked about the forthcoming rise of VLSI, very large-scale integrated circuits with 100,000 to 1,000,000 transistors on them. A major concern with VLSI was the extended man-hours required to design such a large and complicated system. Symbolics intended to produce and sell hardware-accelerated software packages for this. In other words, electronic design automation, or EDA. Dan Liu noted that such a system was developed at Symbolics, and it was pretty good, but never amounted to anything. Another project that Symbolics highlighted early on was applied mathematics, noting that 50,000 mathematicians and scientists used transform math and differential equations daily, doing such calculations by hand. To go after this market, Symbolics licensed a software package first developed at MIT called Maxima, commercializing it and selling it as a product. I believe it is still used somewhat today. Side note, I am slightly bemused by all the parallels to today, especially the part about using LLMs to solve the hardest math problems in the world. Symbolics shipped its first 3600s in 1983 at an entry-level price of $78,500, or about $250,000 today. The 3600s featured several improvements. This included a dedicated tag processor chip that ran alongside the main ALU processor, improved pipelining for better parallelization, and improved ways of garbage collecting. As they ramped up the 3600 and expanded its family, Symbolics kept selling its first-generation LM2s at $70,000 each. They eventually sold 100 of them, which provided good cash flow. So while LMI jumped out of the gate first, Symbolics quickly caught up and surpassed them. By the end of 1983, LMI had sold just 23 machines, and it was clear that Greenblatt's hand production method and bootstrapped style were holding it back. So Greenblatt reluctantly raised outside money. They sold a 25% stake to the semiconductor giant Texas Instruments, licensing them the Lisp software. So Greenblatt was obligated to go down to Texas to teach them how to build the second-generation LMI Lambda machine. LMI continues to struggle in scaling up the hardware, and after a year, TI, frustrated and looking to get into the personal computer industry, essentially forces LMI to give them a license. They then start selling their own Lisp machine, the TI Explorer. Real stab in the back energy here. Greenblatt recalled, "I went down to Texas Instruments several times and basically brought them up to speed on a number of things, and they eventually went in competition and came out with something called the Explorer series. And we didn't really want to be in the hardware business, but unfortunately by this time, the company had been lost control of. The control of the company was in the hands of these venture capitalists and their new presidents who wanted to go into the hardware business." The AI Lisp machine industry was in the midst of a super hot run. In 1984, an industry report found that companies spent about $64 million on AI tools like expert systems and predicted that would grow 50% annually from 1985 to 1990. Small AI startups were all the rage, as large corporations bought into the belief that expert systems do indeed work. In June 1985, a startup called Syntelligence, founded by the team behind Prospector, raised $4.3 million in an oversubscribed round. Lockheed paid $4 million for a stake in Inference Corp at a valuation of $32 million. Inference said that they sold to several big corporates 50 computer programs to be frameworks for trained expert systems for $60,000 each. A few AI startups rushed to the public markets. A notable one was IntelliGenetics, founded in 1980 by the aforementioned Edward Feigenbaum and a number of Stanford Medical School researchers. They started off as a startup building expert systems to help researchers analyze DNA sequences. They then held a $9 million IPO in December 1983. They soon realized that this genetics market was not particularly big. Then in 1984, when the expert systems hype started to ramp up, IntelliGenetics changed their name to IntelliCorp and pivoted to selling expert system quote-unquote shells, expert systems without the knowledge base, kind of like a base model LLM today. They called it the Key Expert System Package. All these AI startups developing these expert systems and the large corporate giants running them needed to buy expensive AI Lisp machines, and that meant a huge pot of money up for grabs in the hardware industry. In 1984, Symbolics generated $40.7 million in revenue, and they started preparing for an IPO. But the rise of the ruthless Texas Instruments giant had them unnerved. TI's scale and a few savvy technical choices let them charge a lower price than what either Symbolics or LMI can do. This capacity was augmented with a few businessman tricks. In October 1984, right before Symbolics was to hold its IPO, Texas Instruments announced that they had sold 400 of its Explorer computers to MIT. Yes, the very place that Symbolics and LMI had spun out of. Turns out that in this deal, MIT only paid for 200 of the 400 TI Explorers. The other 200 were donated, quote unquote, creating an effective price of $27,000 per machine, an insanely lower price than what LMI or Symbolics could ever offer. The TI deal left a sour taste, but Symbolics nevertheless moved forward with its IPO, raising $12 million in November 1984. The following year, 1985, they turned revenue of $69 million, taking 64% of the AI hardware market. The stock almost tripled from its IPO price of $6 to touch $16 in December 1985. The market hit a high in 1986. Symbolics' revenue soared to $114 million, translating to an $11 million profit. In a profile for the Los Angeles Times, Symbolics managers said that they had established a quote-unquote de facto standard in AI. CEO and Chairman Russell Nofsker said, "We started the market, and the market has been growing as fast as we've been able to grow. We don't see a leveling off in the near term. Artificial intelligence is adding a whole new element to the data processing industry. There almost is an unlimited range of opportunities." I admire the timing of such remarks. In the end, this particular AI boom could not last. Part of the boom's end ties back to a general pullback in military spending. The ongoing decline and future disintegration of the Soviet Union shifted DARPA priorities away from AI to other things like autonomous driving. But a lot of the hype was also not panning out. DARPA predicted that AI would soon have human-like capabilities that would let them see, reason, plan, and eventually supervise entire military systems. Now, you need a little hype to sell a grand vision to Congress, I get it. But there was concern early on that expert systems could not live up to the immense hype, and unfortunately they were right. Expert systems fell short. Notably, there was what was called a knowledge acquisition bottleneck. Extracting data from human experts and encoding that into rules was hard and spotty work. There's a lot that experts do that nobody writes down or even thinks about, and we call this tacit knowledge. Moreover, how do you quantify nuanced, ambiguous rules of thumb into cold, hard probabilities? And how do you make sure that you have everything? So expert systems took a long time to create, were difficult to edit, and became extremely brittle in practical use. And as for the big companies and their new AI departments to bring AI into their workflows, that ended up with a bunch of pricey machines they had no idea how to use. One major issue was that the Lisp language never caught on in industry like C did. It was certainly elegant, but suffered a cacophony of dialects and a steep learning curve. Not everyone wants to use recursion or metaprogramming. It also did not play well with other widely used languages in industry. So companies did not have enough Lisp programmers available to make AI programs, or any other programs for that matter, to run on these special use machines. Big flashy corporate AI projects started being quietly canceled or scaled back. What dealt the final and most devastating blow were the Unix workstations. As I mentioned in a prior video, Unix was an operating system developed at AT&T and licensed to universities of the day for free. It became widely used and quite popular. Though these machines did not run Lisp as well as a specialized Lisp machine can, the Unix community developed and shared a wide range of useful Lisp software packages that saved other Unix users time and money. Moreover, the workstation makers benefited from ever faster chips released by the VLSI semiconductor makers like Intel and Motorola. Before long, the chips, compilers, and memories got fast enough to nullify any advantages of buying and running a Lisp machine. The most famous of these general-purpose Unix workstations were those by Sun Microsystems, of course, but also Apollo Computer. Together, they ate Symbolics' lunch. In 1986, Sun said that 6% of its $210 million in revenue came from AI-related applications and growing 50% a year. Symbolics dropped the prices of their computers with a low-end $40,000 unit. Even at that price, however, the somewhat over-engineered Lisp machine could not compete with a Sun workstation priced at a degree lower at just $14,000. Moreover, the Unix software ecosystem was something Symbolics could never overcome. As Dan Liu recalls, no software vendor wanted to build for a shrinking, special-purpose ecosystem. This all happened very fast, and fatally, the company failed to recognize it. Symbolics was full of Lisp academics and perfectionists who spent their entire careers immersed in Lisp. They simply couldn't ever imagine that someone would rather buy and run a Sun. LMI, for their part, had been left far behind by TI's rise and never really recovered from it. They tried to differentiate and survive by pivoting to an original design architecture called the K machine, but they unfortunately went bankrupt in April 1987 before it was ever released. So the Unix workstation killed the Lisp machine. How do you respond to that? In this, Symbolics struggled too thanks to internal divides. One part of the company, led by CEO Novsker, hoped to make and sell an AI chip attachment that workstation vendors can add into their products, enabling users to run Lisp AI programs. Symbolics would then make money by selling software for those. But there was another faction of the company, led by COO Brian Sear, that thought that making chips was a fruitless pursuit of technology leapfrogging, pouring precious money into high-risk revolutionary products rather than working with what was already on the table. They argued that the company pursue a potential new market in computer graphics. Hollywood animation studios like Pixar had noticed that Lisp machines were well suited for producing special effects. Such a strategy would have Symbolics go into a new market, but they'd be selling what they already had. The company needed to choose a path, but management could not decide while Rome burned. In fiscal year 1987, Symbolics reported that it had turned from an $11 million profit to a $25 million loss. Unfortunately, Symbolics had run up its operating costs during the boom. A lot of unnecessary R&D and expensive real estate costs related to chasing both paths. In 1986, at the very peak, they signed 10-year leases on office and factories in California and Massachusetts. The stock price had been falling ever since its peak in December 1985, eventually diving to under $1. In February 1988, the board, apparently unable to decide between Novsker and Sear's directions, ended up asking both to resign. A new president, Ronald Derry, took control. Then came a sledgehammer. In March 1988, Texas Instruments and Apple Computer announced a partnership to create a hybrid workstation called the Micro Explorer. It was a Macintosh 2 with a Lisp machine AI chip installed inside so that it could run Lisp programs. The Micro Explorer was quite powerful, could run Macintosh software, and sold at a stunningly low price of $15,000. FYI, I had no idea this computer ever existed. History is wild. Symbolics, at least a part of it, had been hoping to make this exact product, so the Texas Instruments Apple partnership shook them to the core. It led to a rough round of cost cuts, with 225 of their remaining 640 workers laid off. Just a few years earlier, they once had 1,000. They staggered along for a few years until finally, in 1993, Symbolics filed for bankruptcy and the company liquidated. Its assorted software assets, like its Genera operating system and domain name, the first ever to be registered, were sold off to new owners. One of those owners open sourced the Genera OS, where it and affiliated software packages can be run in emulation on modern hardware like Apple Silicon. An interesting sort of afterlife. Let us end with a love letter to Lisp and these Lisp machines. Lisp is no longer the language of AI. If such a thing exists, it's probably Python. And other languages like Java have absorbed its core ideas. But Lisp itself remains somewhat in use, making it the second oldest programming language of such after Fortran. And as for Symbolics, the business didn't work out, but most people recount that the product was something special. Its employees labored to make an incredible product stuffed with all kinds of impressive features. The software and OS were all in beautifully written Lisp. They even designed and produced their own high-resolution display hardware. In a retrospective session for the Computer History Museum, old Lispers claimed that Lisp machines were the, quote, best development environment ever invented. Another recounted, We continued to develop on Lisp machines until PCs were approximately 50,000 times faster and about 100,000 times cheaper. Anyway, when they finally got the 50,000 times difference, then we regretfully switched to develop on normal machines. Hard to believe, but the plethora of emulators, hobbyist projects, and retained documents/stories about symbolics tell me that there is at least some basis in fact. Lisp remains loved. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.